It is my tremendous pleasure and honor to have as our kickoff speaker of this symposium, which is celebrating the opening of the building of the Andlinger Center, the president of the National Academy of Sciences, Ralph Cicerone. I have known Ralph for I don't know how long, but quite a long time. And, you know, I think there is no better person to give us the lay of the land with respect to where we are on climate change. He gives, as you will see, a beautiful expose of the reason that the Andlinger Center came into being, namely that we are in a situation where the next few decades are key to finding solutions to all of the issues associated with burning fossil fuels and what that's doing in terms of changing our climate. Let me give you a little bit of background about Ralph. So he is the president of the National Academy of Sciences. As I said, he's a world-renowned atmospheric scientist. So he knows of what he speaks. Before he was the president of the National Academy of Sciences, he was at UC Irvine as chancellor, so he has leadership in his bones. He was also, before that, he was at University of Michigan. He was the founding chair, actually, of the Department of Earth Science at UC Irvine. He's won many awards for his work in understanding the climate system, and is obviously a member of the National Academy of Sciences, but he's a member of the American Academy of Arts and Sciences, the American Philosophical Society, he served as the American Geophysical Union president. Again, you know, many different leadership roles, all being concerned throughout his life with respect to the climate and the atmosphere. So please join me in welcoming Professor Ralph Cicerone, President Ralph Cicerone.
Thank you, Professor Carter, Emily, for the invitation to join you today. I was immediately enthusiastic when I heard about the event, although I think that was a year and a half ago. And coming here, you can just sense the enthusiasm. The statement that's being made by creating this center, the Andlinger Center for Energy and the Environment, is a major statement. I think it's one of determination and also some optimism about the future, that there can be solutions, and this place is going to be part of finding solutions as well as generating a lot more basic understanding of the science and engineering of energy and the environment. But in addition to being a big statement, this is also, and this center will provide tangible opportunities for students and faculty to deliver and to engage their interests. So what's not to like about today? Thanks again to everyone who's contributed so much to the concept and the resources to bring this about. What I want to do today is talk about this title that's up here. And here's a brief outline of what I'm going to cover briefly. I'm going to talk about measurements and what's being observed. The observations of climate change all around us in the air and the water, the ice, sea level rise, and so forth. And then, of course, just a very brief statement towards the end of the connections with carbon dioxide from fossil fuel burning. It's actually more than that, but that's a big part of it. I'm not going to talk about predictions today. The good news is there are some real experts here at Princeton, both on the campus and at the Federal NOAA lab in Princeton, who are at the forefront of making predictions about future climate change. So I'll refer you to them. There simply isn't time to cover everything. I wanted to start, as Emily said, with what we're observing. So my first slide is just a very strong, simple statement that you may think it's ironic that I can make this statement, but it's true, that the planetary energy balance dominates global climate change. So the first few things I'm going to talk about, indeed, are the planetary energy balance and what's been observed. This is obviously a cartoon of the Earth being illuminated by the sun, not to scale, of course, but I want to show you some of the numbers. The incoming energy to the Earth is 341 watts per square meter. That's averaged over day and night, averaged over the whole surface of the Earth. And to an extremely good approximation, that is the positive side of the Earth's energy budget. That's what we receive from the sun. About 30% of that number, 100 watts per square meter, is reflected straight back out to space from white surfaces, like the tops of clouds, the snow and ice cover, the ocean at certain angles, light clothing, and so forth. So if you just do the arithmetic, that leaves about 239 watts per square meter on average, averaged over day and night in a year, as I said, that escapes out to space. It's 239 watts, which is absorbed by the Earth atmosphere system, the oceans, and 239 watts, which escapes back out to space. Otherwise, the energy balance wouldn't be. In fact, there is a small energy imbalance now. It's growing. But this just gives you an idea of the numbers. Now, the planet doesn't emit visible light. It emits infrared heat energy, and some of that is intercepted on the way back out through the atmosphere by polyatomic molecules that can interact with infrared radiation, and we can determine those interactions very well in laboratories. And it's been done for many, many years. The Air Force did a great deal of work, academic spectroscopists and so forth. So the existence of chemicals like water vapor and carbon dioxide, ozone, in the Earth's atmosphere create what's called a greenhouse effect. Namely, the energy balance is this. Visible light comes in from the sun, a little bit of infrared, and the loss of energy from the Earth is in the form of infrared radiation, much of which escapes through the air, which is otherwise transparent, but part of it is intercepted by these particular greenhouse gases. One of the first scientific experiments that ever flew on an Earth-orbiting satellite, 1971 or so, was one that looked down at the Earth in the infrared. So these are infrared wavelengths here. And it showed that if the Earth were radiating as just like a blackbody radiator, it would be a smooth curve with respect to wavelength. And what the satellite actually saw instead was a jagged pattern with bites out of the infrared spectrum of energy, where I can't quite see this, but I think that must be ozone at around 10 micrometers. And where is 15 here? I can't read this slide. Yeah. Anyhow, that would be a large carbon dioxide absorption feature. So the point is that you can look down on Earth from outer space and see the greenhouse effect. Now, it's not as quantitative as we want, but this is not a simple theory. It is a simple theory, but it also is observed. In fact, you can calculate what the temperatures of planets should be if you just do this simple energy balance that I've described, and you assume that nothing's changing, so the time derivatives are zero. And what you get is, if you try to calculate this energy balance for Mars, you calculate a temperature which is actually correct, about minus 28 centigrade, plus or minus a few degrees day and night. But if you try the same temperature calculation for Venus, you're off by hundreds of degrees. Now, the little equation here, S is the sunlight energy, alpha is the reflectivity, so 1 minus alpha is what's absorbed. So the incoming light times the fraction that's absorbed has to be equal to the outgoing planetary radiation, which is a physical constant, multiplied by temperature to the fourth. So you'll see S is known, 1 minus alpha is known, sigma is known. All you have to do is solve that equation for temperature, and this is what you get. For Earth, you calculate that the temperature is something like 0 degrees Fahrenheit all the time, everywhere. And that's not correct. In fact, it's not completely clear that Earth was ever completely frozen over, but it's certainly wrong today. And what's wrong with this calculation is we are leaving out the greenhouse effect and the way the radiation, the energy really bounces around. We have to take into account the presence of clouds and the greenhouse effect to get Earth's temperature right. Okay, so what's the big deal? the observed record of carbon dioxide measurements in Earth's air, if you go to the cleanest places you can find and measure carbon dioxide, as this, in this case, from the Keeling family, started in the late 50s through 2015. This particular record, the black dots come from Mauna Loa, Hawaii, at about 11,000 feet above sea level. Each black dot is the average of a month's measurements taken about every hour. So every hour for a month, and then you get a black dot on the curve. And the red curve happens to be the South Pole with a different setup. But what you can see, the overwhelming message here is that the amount of carbon dioxide in air, in clean air, not polluted air, has risen from about 312, 315 parts per million to 400 in this 50-year period. It's also very interesting, and there are people who here at Princeton who know a lot about this. What are the wiggles? The up and down wiggles that are observed every year. Well, in the, for example, the Northern Hemisphere, but it's true in the Southern Hemisphere also. In spring and summer, photosynthesis draws CO2 out of the atmosphere, so the CO2 goes down a little bit, and then in fall and winter, dying organisms and leaf debris and so forth release carbon dioxide through not only respiration but decay, so that there's an annual cycle, up and down, but the underlying trend is definitely up. As it turns out, most of this carbon dioxide, nearly all of it, is from fossil fuel burning. That is the excess that we're seeing, and I'll explain that as I go along. So now let's say, what are we seeing about the climate system with that very brief introduction? This set of temperature measurements probably now includes about 500 million data points from around the world. And 0 on this graph is not 0 degrees centigrade or Fahrenheit. It's the, here we are, it's the, an average of a 30-year period from 1951 to 80. So we need a reference period. So 0 is that reference period. That is, what are the world average temperatures during that 30-year period? Anything below that line is colder than that 30-year average. Anything above it is warmer than the 30-year average. I'll show you a lot more about this, but what you see is, for example, the last dot, the annual global average day and night and everything averaged out for 2015 is the highest ever. 2014 was the next highest, and so forth. 1998, which was a big El Nino year, was fairly high, but there's an underlying trend which keeps going up. And I'll tell you a little bit more about this record as we go along. The data are so voluminous from all around the world that people, and these data are from the NASA GISS Center in New York City, you can create a map of all around the world and then with a false color chart show whether the temperatures are much higher than what was observed in the 50s, 60s, and 70s, or much lower in the blue. And then, so what's plotted here are 3 different years. The warmest year of all so far is 2016. 2015 is the second warmest ever, and so forth, compared to an interesting chart here where 1 is January, 2 is February, 12 is December. So for every month of the year, what's plotted here is the all-time record. So the all-time record for June was this around the world, and so forth back to January. And the temperature anomaly, that is the amount above normal, so to speak, for 2016 is the highest of all. There have been something like 9 months in a row, 10 months in a row worldwide now, where the temperatures have broken records from all the previous 130 years worth of data. This is just to show you the kind of data that are available. There are wiggles as you go along. We're certainly experiencing a cold, rainy session right now on the East Coast. And in fact, when you look at these records in some detail, for example, 2015, there's this big blue spot not too far from the East Coast of the United States, showing that it was colder than normal there. So these things happen. To break up the data in a different way, we can examine the data north of the equator and south of the equator. All of this is at the surface level of the Earth, I should say. And you can see that back 130 years again, on the same scale. The southern hemisphere is rising, but less than the northern hemisphere. They've been sometimes in more or less lockstep, other times kind of out of phase with each other, not to be surprised. The reason we do it north and south is, generally speaking, the circulation patterns around the Earth are east to west. So there is some separation at the equator. Another reason is that because there's so much more water in the southern hemisphere, you would expect, if the Earth is being warmed somehow, that there should be a slower warming in the southern hemisphere, and indeed you see it. The southern hemisphere is responding because we believe this is being forced, in fact, by human activities, but that's exactly what you see in the actual data. The northern hemisphere is a little more variable, there's less heat capacity, and under the forcing, it's heating up faster. The temperature is rising faster. Now, water. It's harder to measure temperatures around the world in water than it is the air. For one reason, we don't have commercial aircraft flying around like we do through the atmosphere. The air is better monitored. There's weather prediction going on all over the place, balloons and thermometers and satellite instruments, but over the ocean there's less data. So it's only in the last few years that enough data have started to become available of world ocean temperatures to be able to see the heat now building up in the world's oceans. So this graph shows 3 or 4 different profiles versus depth. So this is the top of the ocean down a couple kilometers deep, 2,000 meters deep, showing on the left-right axis the extra heat that's being observed in those water columns now from the top down to the bottom of the ocean that has accumulated, or the difference has been seen in the last 50 years. In some cases, the oceans haven't been very well covered, as I said, but these data are now really taking shape to the point that we can see the extra heat from the atmosphere diffusing, being conducted down and carried down in overturning activity into the deeper waters than people really know how to calculate. So this graph, in fact, shows the world ocean heat content in a couple of different layers, so to speak. The upper layers, which are shown in this curve, which is the so-called mixed layer of the oceans down to 700 meters. This curve shows the extra heat absorbed versus date down to 2,000 meters. And then this graph shows the fraction of the world oceans that are being covered at all. And fortunately, the coverage of the world oceans is now getting close to 100%, roughly speaking, of what we need to get a proper sense of what's happening and good numbers. I'm just going to say one word about Arctic sea ice, although there's a lot to say. There are different ways to look at the data, but it has been measured now, the sea ice extent. This is the floating ice. It has been measured well enough now for about 35 years to get trends. This one happens to be one of the smaller trends, namely the amount of sea ice floating in the Arctic measured in terms of square kilometers in the month of January every year from 1979 to 2016. And indeed, it's decreasing. The summer values are more pronounced. The tendency toward a sea ice-free, that is an ice-free Arctic Ocean, is growing in the summertime. And that has large implications for commerce, for military operations, and for shore coastal activities of all kinds around the Arctic countries. So this is a significant event. It's not completely clear why it's happening, but certainly the Arctic, if you recall a couple of figures ago, the Arctic areas are warming up faster. You see colors around the Arctic latitudes here, 90 degrees north, that you don't see anywhere else. This dark red, even some emerging of this pink color, which is 7 degrees Celsius above normal or something for those periods of time. So the Arctic sea ice is decreasing. There are many more measures. Unfortunately, one of the sensors that's been measuring this, you can go to a website and see the new data every day of the year, from an old military satellite, has now failed. The data stopped coming in about April 1st. after 35, 36 years. So I'm not sure what's going to replace this data record. Now for some of the more dramatic ones. The amount of ice measured in billion tons that sits on the the Greenland ice sheet. So it's a continent. So the ice that's sitting on that continent will cause sea level to rise if it reaches the ocean, either as ice or as melted water. And in fact, we now have a record of really interesting measurements. I wish there were 20 minutes more so I could give you the background on how these measurements are made, but they are not made with cameras and sextants the way our predecessors would have. These are measured with a really high-tech device which senses the slight change in the Earth's gravitational pull as a satellite goes over from orbit to orbit to orbit. And after enough orbits, the satellite can actually measure the different gravitational pull if the mass beneath it is changing. This instrument has now measured the difference in groundwater in the Indian subcontinent with season. It's just unbelievable, important for water resources and hydrology. But for these ice measurements, it's spectacular. Isabella Vellaconia, Isabella Vellaconia gave me this slide. She just updated it. But when her data series started with her colleague John Moir, who's recently died, there were only 3 years of data, so nobody really knew what to make out of these. Now they've extended it to 2016. So they have measured about as well as anything could do the amount of ice locked on the Greenland continent. And the annual decrease averaged over this time is 270 gigatons per year. But what's more interesting is the best fit to the data is an upside-down parabola. There's an acceleration rate. The rate of ice loss from Greenland is itself increasing, so its contribution to sea level rise is increasing. The Antarctic data are shown on the next slide, and although the overall rate of loss from Antarctica, if you average over the whole continent, is less, it's only about 85 billion tons per year, its acceleration rate is significant. You can see that this is not a straight line. The acceleration rate of this ice loss is significant. Now, they've refined this instrument to the point that they can now do individual sections of Antarctica and Greenland. They can tell you which quadrants or which sectors of those continents are experiencing ice loss versus ice gain. So, for example, you can see the annual cycles here of during the Antarctic winter, there's an accumulation of snow and ice, and then it decreases in the melting season and so forth every year. It's clearer in Greenland. These are spectacular data. Well, what does it mean for sea level rise? The record of sea level measurements is a very difficult one. So this record goes back, you can see, about 100 years from 1980, maybe 110 years. And it was done by very carefully measuring the height at which seawater will mark a pole that's pounded into a coastal line somewhere around the world. So it was a little bit crude, but people worked at it very hard. And this is probably a decent global average, showing in that 100 years a rise of sea level of about 16 centimeters, so that the average rate was about 1.6 millimeters a year. The red part of the curve, though, represents where we are now. And by the way, this record has been slightly revised recently, but I won't go into that today. The modern record is that last period from 1992 until now, where the measurements are done by Earth-orbiting satellites using laser altimeters. So they're getting the sea level height measurements very accurately now, more precisely, and a better geographical average. And what they're finding is a rate of sea level rise which is twice as big. It's 3.4 millimeters per year instead of being 1.6. So people are still trying to figure out whether this represents an accelerated rate of sea level rise or whether the previous record was a little too approximate, or both. And I won't go into the details today, but the point is now we have accurate measurements of sea level rise, and the numbers are adding up now. 8 and 10 years ago, we couldn't get the numbers to add up. That is, where is this sea level rise coming from? Is it coming from melting ice and calving icebergs? Or is it coming from the expansion of seawater, which occurs when it's heated? You do get a slight expansion of water when you heat it. Or is it some other purpose? Well, now the numbers add up reasonably well, so we can account for this 3.4 millimeters per year coming from Antarctica, Greenland, inland continents, and seawater expansion. Let me go back to carbon dioxide now. What's been happening with carbon dioxide? Well, first of all, what is the evidence that this carbon dioxide increase is due to human activities and fossil fuel burning? There are all kinds of pieces of evidence, but one of the most dramatic is now about nearly 30 years old piece of evidence where a group of scientists, French, Danish, Soviet, and Russian, maybe a couple of other countries, drilled down into old ice cores which can be dated. So going from the modern current time in ice back 100,000 years, 200,000 years, all the way back to 450,000 years. And they were able to interrogate that ice. So after dating it, that is, how old is it from beneath the surface of the ice, they can interrogate what are the gases trapped in that ice with which the ice was in contact when it first formed. And doing that, they've been able to extract what is the time history of carbon dioxide. This is a direct physical measurement. This is not a computer model. And what they find is that obviously there have been some ice ages, which I'll just point to, because on the left-hand scale is temperature. So when temperature is low, this was an ice age, this was an ice age, an ice age. So the last ice age was approximately 20,000 years ago, going back to 140,000 years ago, and so forth. And when the world was cold, the carbon dioxide levels were about 180 parts per million, which is up on this graph. When the world was warm in between ice ages, the carbon dioxide amounts were about 280 parts per million. So whatever has caused this over the last 4 major ice ages, in fact, the record now goes back to 800,000 years, so it's more than 4 ice ages, whatever caused it, we are now out of these natural ranges. The carbon dioxide amounts today at 400 part per million are up here somewhere, whereas the top on all of these previous records was 180 parts per million. There are some very interesting questions about what happened first. Each time the world warmed up, was it due to increased carbon dioxide in the air, or was the carbon dioxide lagging the increased temperature? And I can talk about that later, because now the time resolution is getting large enough, good enough, to be able to distinguish whether the carbon dioxide rose first or the temperature rose first. Also on this graph is one of the other greenhouse gases, methane, where the behavior is the same. What it all means is that we really are perturbing the Earth's energy budget. If you take those increases that have been observed now in these greenhouse gases, we're changing the Earth's energy budget at the surface by about 3 watts per square meter, which is about 1.25% of the incoming sun. I remember the first I ever read about climate change in an encyclopedia 40 years ago was that if the sun were ever to change its output by 1%, there would be a major climate change of some kind. And now this is happening, only it's happening in a period of decades rather than geologic time history. Just to give you a feeling for the numbers, all human energy use, if you add it all up, nuclear power, coal burning, oil burning, gas burning, wood burning, all the hydrothermal power, all the wind and solar energy, if you would say, let's just dissipate that over the whole Earth, the density we would get is about 1/40 of a watt per square meter. The extra heat trapped by the greenhouse gases is about 100 times larger, and then that in turn is the sun's incoming energy. So if you were trying to warm up this planet or change its climate, and you wanted to do that by more human fuel burning and more human energy use, you can't do it. The number is just too small. But this greenhouse effect provides a big amplifier. that we didn't anticipate. Well, what's the evidence that it's from human activity? First of all, the last 30-year period of human history has been unique in another sense. People have been able to measure the output from the sun, the energy that heats the planet, well enough to be able to say whether it's changed or not. This work is from a woman named Judith Lean at the Naval Research Laboratory and a colleague of hers in Switzerland. So they've strung together a lot of measurements from satellites and even some ground-based observatories. And what they find is that the output from the sun has an 11-year cycle to it, which is what people kind of guessed in the first place. Although, if they had shown that the output of the sun had increased over this 30-year period, it would have been interesting, because then we'd be dealing with climate change due to some other force, not humans. So some of us were a little disappointed that this is what turned out, but that's what. And this is now their data extended over another solar cycle. So the evidence is pretty strong that the sun's output has not increased. Therefore, people who say that whatever is happening now is just something natural, the sun's activity, they don't have a leg to stand on anymore. We have evidence that says that that's incorrect. Just a few words on the evidence that the CO2 is from fossil fuels. There's no simple way to say, yes, this absolutely proves it. But first of all, the time history of the CO2 increase that's been measured in air and that of fossil fuel usage. The big increase in fossil fuel usage has been in the past century, even more recent than that. It certainly overlaps pretty well with what's observed with CO2 in the atmosphere. The amounts of the increase are within a factor of 2 of what's understood. It seems that the oceans are absorbing a quarter to a half of the energy, so and of the CO2 itself. So this holds. I want to just jump down to the bottom too. The isotopic contents of carbon molecules in CO2 have moved in the direction of fossil fuels, creating the excess carbon dioxide. And then finally, the most elegant of all, and there's someone here at Princeton who has done some of this work, Michael Bender. But this is a record of measuring atmospheric oxygen over the last 20 or 30 years. There are actually about 8 places around the world where they've done this. And they find that the amount of oxygen, if you can measure it well enough to 6 decimal points, this is what you find, that the oxygen contents are decreasing roughly in parts per million. And if nothing else were happening except burning fossil fuels, you get a yellow line. In other words, if oxygen were just an inert gas, except for burning, and you would take oxygen out of air and make CO2 out of it, you would get this yellow line. Instead, the real data are decreasing, oxygen is decreasing slower than that, and a likely explanation is that the greening of the Earth's biota, being fertilized marginally by CO2, is increasing the rate of photosynthesis in some gross sense. So the rate of fall off, but to a first approximation, that's pretty close, showing that the CO2 increase is from the burning of fossil fuels in this case, and the oxygen decrease being consumed that way. Just a couple of quick words. If you look at trends in global carbon dioxide emissions, just very quickly, I've got a couple of graphs. The global figure shows that we're releasing about 10 billion tons a year of carbon dioxide, of carbon in the form of carbon dioxide. And there's some breakdowns on these next couple of curves that all of you here have on, coal burning, oil burning, gas, and so forth. I had 2 more graphs and then I'll stop. This one, so the evidence is that the CO2 increase is from human activities, perhaps 85% of it from fossil fuel burning and perhaps 15% from deforestation, the burning of wood, clearing for agriculture, and the decomposition of soil organic matter. That number is more uncertain. Why is it that people are talking about decreasing our input, our use of fossil fuels by maybe 80%? Where did that number come from? Is it a political goal? Well, it might be, but the physical basis of it, you can write down the appropriate differential equations and get the answer. But this cartoon I have from a Japanese colleague is something I like. The level of water in the bathtub represents carbon dioxide in the atmosphere. The rate of input is simply the faucet rate, and the rate of draining the bathtub, in this case, is limited by the natural drawdown processes of carbon dioxide. Uptake and storage by plants, for example, absorption by the oceans into deep water that's not going to come back to the air for a long time. Well, these sinks, so to speak, are measured to be about 3 gigatons of carbon a year. That's a pretty good number, certainly within, say, a third. The rate of increase from this old cartoon was 7 billion tons a year. We're now at about 10. And if you count the high end of the forest rates, it's probably 11 or 12. So the ratio of what nature can absorb to the input is maybe 20% or a quarter. And that's where the figure comes from, of the need to just simply stabilize carbon dioxide in the air, not to decrease it, just to stabilize it. Don't let it increase beyond 400 parts per million. We would have to decrease the input by about 70 or 80%. So that's where the figure comes from. My last figure is another kind of data, sorry. If you take the temperature data I've shown now, the real human impact will come from not just average temperatures, but extreme temperatures, and of course severe storms and sea level rise, and the distribution of the seasons, the length of growing season, all of those things. But just to give you the closest part of that we can see, these are distribution diagrams, like a Gaussian or normal distribution, of the temperatures in the northern hemisphere, and in the top, it's summertime northern hemisphere. So this is what the distribution looked like in the 1950s, with the blue representing kind of the bottom 1/3 of the temperature distribution. These are measured in standard deviations of averages, but the point is it's essentially temperature running left to right. By the 1960s, you could see that the northern hemisphere summer temperatures had moved to the right. We're now seeing more high temperatures, fewer low temperatures. And by this last decade, 2005 to 2015, the whole distribution is moved significantly to the right of where it was then. Well, yeah, you can see this in records, but consider the extreme side here. If you take a point on the right side, say out 3 or 4 standard deviations, we're now getting like 35% more of those temperatures than we did in the 50s. And it's just the long tail. So if you pick a point off to the right of the normal distribution and ask how many more of those extreme events are we getting, the answer is it's really increasing quickly. The insurance companies and the reinsurance companies of the world know this stuff. Their payments for claims, for example, to extreme weather events, and of course that includes storms and rainfall and floods and so forth, they're very wary about what's happening to these distributions. So the bottom is simply a repeat of that curve, but for the winter months, showing similar movement to the right. So I'll stop there. There's so much more to talk about what's actually predicted and how reliable or unreliable it is. Things are getting better. But the observations alone tell us that the effects we're being seen now are serious. They're getting better documented. The more we measure, the more we find changing. And it implies that we really have to keep going on this research to be able to see the changes developing, to be able to allow humans to build a better case for mitigation, that is, lowering the driving forces, but also adapting to whatever changes are coming. So let me stop there. Thank you very much. Oh, sure.
So we will take questions, but before we take questions, I have a small gift, 2 gifts from the Andlinger Center to you.
Wow.
For educating everyone in this room with the latest data and showing that it's not a fantasy, it's happening, and that there is laying out the powerful case really for the rest of our symposium about how important it is to get moving.
Thanks, Emily.
So thank you very much.
My name tag identifies me as a Princeton parent, so if someone else sees this, they might disappear.
So questions? I think we have microphones ready. Yeah.
Thank you very much for the great presentation. I'm Wei Pan. I'm a grad student here on campus. I'm wondering, given that you already talked about the evidence is getting better and better now, do you think this is also making the scientific community more powerful than before to influence the policy-making process? Do you see that happening? Do you see that changing in recent years comparing with...
I missed a few words when you referred to the scientific community. Could you repeat that part of it?
Yeah, sure. So my question is, given that we have better measurement data these days, do you think this is also making the scientific community more powerful than before to influence the policy-making process around climate change?
I do. I think the political partisanship that's developed in the United States was totally unpredictable. It's very odd. Historically, the Republicans have a strong record of supporting basic research. It was under President Nixon that the EPA was created, NEPA and so forth, with Bill Riley and Bill Ruckelshaus House EPA administrators, for example. So what's happened is, to me, it's unpredictable. I don't think it's sustainable. I think the evidence will be driving this debate more and more and more. On the other hand, you may have read in yesterday's newspapers that Australia, which is home to some of the world's best weather and climate scientists, has just fired 350 of them because they want those people to work on commercial products instead. And a couple of the world's experts on measuring ocean temperatures happen to be in Australia. So there are these strange things going on, but I'm basically optimistic. Emily and I went together to speak to a group of senators privately several years ago. The evening itself wasn't a spectacular success, but in talking to them privately, you can sense that they're trying to pay attention to what's really happening. I'm optimistic about it.
Thank you. My name is Mitchell Small. I'm a visiting faculty member in the Andlinger Center. I hadn't been aware of the decreasing oxygen levels in the atmosphere. Does that have implications in and of itself, like ocean acidification has, its own implications?
I don't think so, not on any short time scale. The time constants involved with atmospheric oxygen are tens of thousands of years. For example, if you were to burn all the available surface vegetation around the Earth and throw in some fossil fuels, I think you could only reduce oxygen by about 1%. The levels of low oxygen that are being seen in dead zones in the world's estuaries and bays and oceans are due to local contamination, loading organic material into the waters and so forth. The measurement of oxygen, though, is just a world-class achievement. Is Mike Bender here? Because he knows this better than I do, but the person who did this, Ralph Keeling, was finishing his PhD in applied physics. It was at Harvard in 1986. And he had proposed making this measurement using an interferometric technique. But the analytical chemistry involved in it is just superb. Well, during the World Series in 1986, he first got his experiment to work well. And during the sixth game, when Boston was in the World Series, traffic stopped. And there were some refreshing breezes from the west coming into Boston with no traffic, no combustion going on. And the oxygen levels just went way up in his measurement. So he knew he had it then.
Japanese bathtub slide. You said, I think it was 3.1 gigatons per year.
Yeah, roughly.
We're producing about 10, and you said, so if we knock it down by 7, we'll be at par. I didn't understand that. It seems to me if you knock it down by 7, you're in a break even. But in a natural environment, fossil fuel emissions are essentially zero, so that 3.1 gigaton absorption would go on normally.
You're absolutely right. The numbers, especially the CO2 uptake by land areas, is still pretty uncertain. It may even vary decade to decade. So there is some slop in those calculations. But the more refined calculations probably do end up with 70 to 80% as the net of how much we would have to decrease the fossil fuel contribution. But that slide was pretty much a cartoon.
So if we took it to zero, does that mean that ocean absorption would actually result in a decrease in carbon dioxide?
Yes. Averaged over enough time. That's right. because everything else is probably pretty well equilibrated around the saturation pressure of CO2 and ocean photosynthesis. It's not guaranteed that there would be a drag down, but there probably would be some, with a time constant of maybe 1,000 years.
Hello, Ed Saliga, class of 75, an engineer here from Princeton. I run a solar power company. Appreciate that we're just looking at data, and it's so clear, but I'd like to just see if there's any indication that links it to policy on the topic of thermal inertia, in terms of, if we were beginning to make some changes in CO2 emissions, is there any indication in the data that says what that time frame might look like?
We can tell by the current state of energy imbalance of the planet, the fact that the Earth is not absorbing exactly as much energy coming in, that even if we stopped the release of fossil fuel CO2 now, there would be a period of some decades where things would keep warming up to reach a neutral point on the energy balance. So a period of decades, maybe 40 or 50 years of increased warming.
Thank you.
The real crunch is on the ice balance of Antarctica and Greenland, where what's been learned in the last 7 or 8 years is very dramatic. There are only a few spots where ice is sliding off the continents and then being undercut by warm water below and being melted. So the good news is people can now focus on those few spots around Antarctica and Greenland where it's happening, try to understand the mechanics, the topography, and the relative amounts of ocean heat versus simply breaking off of ice. And it's not encouraging what they're finding, but it's worth the investigation because that is an irreversible process. The only other irreversible process that comes to mind would be biological extinction. So from a policy point of view, if you want to take out some precautionary work, I think you'd be driven by these two irreversible factors, the rise in sea level and the loss of biological diversity. And then ocean acidification comes into that also.
Are there any advantages to global warming, like increased arable land and increased crop yields? In other words, are we benefiting from global warming?
There almost certainly are. There are a few economists who are actually trying to do cost-benefit calculations based on actual crop yields, on elongated growing seasons, on the temperature responses of plants. One of them, Bill Nordhaus at Yale, who I think probably does more of this work than anybody else, thinks that for some crops we could be entering into a slightly beneficial range for the next couple of decades, but not very many places and not very many crops. So on the whole, this is a losing proposition. There was a dominant Soviet in the Soviet era, scientists in the Soviet Union who convinced the Soviet leaders that climate change was a winning proposition for them because they would have longer growing seasons. But it was a very shaky proposition then, and it's probably more shaky now because of the melting of the permafrost, which is going on.
Another question? Yeah, Forrest?
Hi, Forrest Magers. I'm one of the joint appointments between architecture and the Andlinger Center. And I'm curious, I talk to my students a lot about the concept of mitigation, and thank you so much for the very informative presentation of all the up-to-date CO2 challenges that we face. And I'm curious what your outlook is in the context of this mitigation of these challenges in terms of how to slow down this rise in CO2 and the heat in the ocean and all these various components that we're understanding better and better, or whether you see, if we plan for the future today, how much would you design for adapting to some of the extreme things that we know are coming, and how much would you design for mitigating the problems that we're causing? Do you see a pathway that's clear in one direction?
So I think they're both valuable and necessary. And you can see the way certain companies are positioning themselves for the future, that they're making investments that they're counting on. And again, if you talk to the reinsurance companies, if they'll be open with you, they'll tell you what a lot of companies are doing under their pressure. So there's some optimism there. In the short term, I think energy efficiency has enormous gains yet for pretty much the whole world. And I know some people here are working on some new techniques and devices. In the longer term, I think basic energy research is really needed because energy is such an important commodity. It's pervasive, everybody needs it. We can't just give up on energy. So, but I do think mitigation and adaptation are needed.
Forrest is one of those people that is working on energy efficiency
Good.
in the Andlinger Center. Other questions? Yes, another of our joint faculty.
Hello, Egeman Coleman, one of the joint faculty, and I've been teaching a course on climate engineering, so I have to ask this. And you had a report on climate engineering. So how would you put that in the context of adaptation and mitigation? I mean, there was an NAS report that came out a few years back, but did anything change since then?
The adaptation picture, I think, is really very local because, just as an example with sea level rise, there are places that are experiencing more or less sea level rise than the average because of underlying geological activity. A good example is Norfolk and Hampton Roads in Virginia, where they're really experiencing a lot more storm surges and damage due to the settling of the local land. And places in Florida where you've got groundwater intrusion, they're experiencing more problems and sea level percolating horizontally. So I think mitigation issues are going to be very local. I remember 30 years ago being approached by a lumber company that was doing a lot of paper mill production, and they had to decide whether to keep their paper mills along a certain northwest river. And what they decided to do, based on the early evidence, was simply move their operations upstream to a couple of meters higher above sea level. So there will be a lot of local decisions like that, where depending on the time horizons that people believe they have to function in and their investment portfolio, they can make really good local decisions or they can blow it. The legislature and governor in North Carolina 3 or so years ago outlawed any attention to sea level rise in public planning in North Carolina. What can you say? I think it was overturned shortly thereafter, but I think on the plus side, we will see more local actions because people know what's happening. They can see it.
Actually, I think as a possible clarification, I think what he was wondering about is your views on and you can correct me if I'm wrong, about geoengineering.
Is that what you said?
Yeah.
Thank you.
What is your opinion about geoengineering?
See,
and for those of you that don't necessarily know what that is referring to, it's referring to manipulating the climate to essentially bring back down the temperature potentially.
well, that shows that you're deemed to be starting, I guess, in July. She's a good listener. Yeah, there have been several ideas proposed about ways that we could engineer the face of the Earth in some way to slow down climate change or even to negate it. One of the best ideas was to fertilize parts of the world's oceans with iron. There is evidence that the productivity of parts of the world's oceans are limited by iron amounts. And some people here at Princeton did some very, very good calculations 20 years ago trying to sort through it. And there have been some experiments done in the open ocean. How much more photosynthesis can you get to happen if you supply this limiting nutrient? And the answer was they could achieve and observe blooms of phytoplankton and photosynthetic organisms in the ocean, drawing CO2 down faster. The problem is you have to get the stuff to sink deep into the ocean so that the carbon doesn't get reoxidized to simply become CO2 again, and that's never been achieved. So people have more or less given up on the idea, but it was a good one. It was called the Geritol solution. The ideas that are more current now, which are not being explored experimentally, are to place reflective material up high in the atmosphere, in the stratosphere, where it can stay aloft for a period of 1 to 5 years and reflect sunlight back out to space. It's our Academy report last year, it was chaired by Marcia McNutt, concluded that that result, or that method, could be cheap, it could be deployed. It's cheap enough to be deployed by individual countries or even individual wealthy people, but it's dangerous. because the list of potential side effects is long and complicated. For example, would the effect be localized? Or what would happen to rainfall systems and so forth? The gentler approach would be to try to suck carbon dioxide out of the atmosphere, simply to do a bulk removal of carbon dioxide from the world's atmosphere. The contrast by Marcia McNutt's report was that this would be probably safe, it would be slow, the results wouldn't be seen quickly, and it would be expensive. Now, maybe there's better technology. Generally speaking, though, you can see calculatable differences to the Earth's energy budget by any one of these techniques, but it looks like iron fertilization is not strong enough. Solar radiation management, so to speak, the reflective material in the stratosphere, is very powerful, but perhaps uncontrollable, and it would have to be repeated every few years. And you still have ocean acidification to worry about, because if we continue just to raise the carbon dioxide amounts in the air, keep the planet cool some other way, the oceans still acidify, and so forth. I'm waving my hand because there haven't been many good calculations or no experiments at all on these topics.
Thank you very much,
Okay,
Ralph.
thanks, Emily.